It drifted into our solar system, like an uninvited guest who doesn't knock. Mysterious, quiet, and carrying a name that sounds more like a Wi-Fi password than an astronomical discovery, 3IATLAS. It didn't send a postcard. It didn't check in on social media. And before we could even get a good look at it, it was already on its way out, leaving scientists blinking, telescopes straining, and everyone else wondering what exactly just passed through our cosmic neighborhood. For context, 3IATLAS wasn't our first interstellar visitor. Before it came Oumuamua, the elongated, shiny object that looked suspiciously like an alien probe, or, depending on who you ask, a cosmic breadstick. Then there was Borisov, a much more well-behaved comet, icy, glowing, and doing all the normal comet things. But 3IATLAS was different. It showed up in 2020, tried to make an entrance, and then fell apart. Literally. As in, I just got here, but I'm already disintegrating. Talk about a dramatic arrival. Good evening, curious minds. Science doesn't need to shout to be fascinating. Sometimes it's best enjoyed the way you'd enjoy a late-night conversation. Quietly, with a cup of tea, and maybe the soft hum of a fan in the background. Before we begin, leave a comment and tell me where and when you're tuning in. And if you find yourself learning something new, as you drift towards sleep, consider subscribing. No pressure, only if you enjoy these calm journeys through the universe. Now, let's begin. Astronomers named it 3I because it was the third interstellar object we'd ever seen. And Atlas because it was discovered by the Asteroid Terrestrial Impact Last Alert System, which, by the way, sounds like the kind of system you only activate when things are about to go very wrong. Its orbit told us one thing for certain. It didn't belong here. Its path wasn't elliptical, like planets or comets born in our sun's domain. It was hyperbolic, meaning it was just passing through, a cosmic tourist, or maybe a delivery gone wrong. Because what if, just what if, 3IATLAS wasn't just a rock from another system? What if it was something more tragic? A failed planet seed, a chunk of material that once had dreams of growing up to be a world, but never got the chance. Imagine being formed in the dusty nursery of a newborn star, surrounded by swirling gas and ice, only to be yeeted out of your home system before you could even build an atmosphere. Galactic eviction notice served. See, planet formation is a messy business. Stars form in clouds of gas and dust, and those same clouds leave behind leftover crumbs, disks where little grains start sticking together. Sometimes those grains get lucky. They clump, grow, collide, and eventually become planets. But most of them don't make it. Most are tossed aside, shattered, or flung into interstellar space by the chaotic gravity of bigger siblings. If the universe had a lost and found box, it would be full of these poor, half-formed rejects drifting between the stars. And maybe 3IATLAS was one of them. That's the fun part about these interstellar interlopers. We know so little that speculation becomes a playground. Its brightness hinted at dust, maybe volatile ices, maybe even some organic material baked by countless eons of radiation. But it broke apart too soon for us to confirm much. It's like trying to analyze a cake that exploded in the oven. We got a few crumbs, a whiff of something sweet, and a lot of questions. But the timing was interesting. It appeared not long after Oumuamua had already stirred public imagination with talk of alien tech. People were primed for mystery. When 3IATLAS came along, some hoped for another headline. Interstellar Visitor 2, the sequel. Instead, it was more of a short film. By the time telescopes locked on, its brightness faded, its nucleus split, and its pieces scattered like cosmic confetti. It was the celestial equivalent of someone dropping their phone on arrival, screen shattered, and then leaving before anyone could say hello. Still, even in its failure, it told us something profound. The fact that we've seen 3 of these visitors in such a short time, after billions of years of not noticing any, means our technology is finally good enough to spot them. We are catching glimpses of the interstellar driftwood that connects all star systems, tiny relics from worlds that could have been. Each one carries a story written in elements and isotopes, a kind of universal signature of how planets are made, and sometimes how they're unmade. Think of it this way: our solar system isn't a sealed bubble. It's more like a neighborhood on a galactic highway. Occasionally, someone's trash blows into our yard, and that trash can be priceless. These stray objects are messengers from the unknown, proof that other stars have their own chaos, their own failures, their own stories of creation and destruction. And every now and then, one of those stories drifts close enough for us to catch a glimpse before it vanishes again into the dark. That's what makes 3IATLAS so compelling. It wasn't flashy like a comet or sleek like Oumuamua. It was fragile, fleeting, and strangely relatable. A little piece of cosmic ambition that didn't quite work out. Maybe it was supposed to grow into a planet orbiting some distant red sun. Maybe it carried the ingredients for oceans, for clouds, even for life. But fate had other plans. Gravity misfired, and out it went, tumbling into the interstellar void. So here it was, millions of years later, brushing past our solar system for a few brief weeks before fading from sight. A failed world seed, crossing paths with a planet that did make it. Us. If that doesn't make you feel poetic or slightly sentimental toward a space rock, nothing will. Because maybe the real story of 3IATLAS isn't that it failed to become a planet. Maybe it succeeded in something else entirely, reminding us that every world, every star, every tiny piece of cosmic debris has a history. And sometimes that history drifts by just long enough for us to wonder. And that's where our question begins. Not with a rock, but with a what if? What if 3IATLAS was a seed that never sprouted? What does that say about the universe's creative process? And about us, the ones lucky enough to watch? If space had a junk drawer, it would be full to bursting. Old comets, half-finished asteroids, shards of ancient collisions, and somewhere in there, drifting between the stars, are the true misfits, the interstellar objects. These are the rocks that didn't stay where they were born, the ones ejected from their home solar systems, like teenagers told to find their own place. They wander the galaxy, not belonging anywhere, and every so often, one drifts close enough to a curious species like us for a brief cameo before fading back into the dark. It's tempting to think of space as empty, a clean vacuum between suns. It's not. Space is messy. There are clouds of dust the size of entire solar systems, rivers of gas stretching across light years, and debris fields left behind by star births and deaths. The galaxy is basically one enormous construction zone that's been going on for 14 billion years, and no one's cleaned up since. Or, as one astronomer once joked, space isn't empty, it's just untidy. Think of it as the universe's lost and found box. Every interstellar object starts somewhere, in the heart of a forming solar system. Picture a young star surrounded by a swirling disk of gas, ice, and rock. It's like a cosmic soup where gravity stirs the ingredients. Tiny grains of dust bump into each other, stick, and grow. Some of those clumps will eventually become planets. But the process isn't graceful. It's more like a demolition derby in slow motion. Collisions are constant, gravity is chaotic, and everything is fighting for orbital real estate. In the end, a lot of material just doesn't make the cut. That's how rogues are born. A developing planet might pull too hard on a smaller object, slingshotting it out of the system entirely. A passing star might tug the outer debris cloud and scatter chunks across interstellar space. Sometimes it's just bad luck. A collision at the wrong time, a gravitational nudge from a gas giant, and suddenly you're flung into the void at thousands of kilometers per second. 1 minute, you're part of a happy little planetary family. The next, you're on an unplanned, one-way trip through eternity. And it's not a rare occurrence. Scientists estimate that for every planetary system like ours, there could be billions of rogue objects wandering the galaxy, fragments of worlds that never formed, or leftovers from those that did. Think of them as the crumbs of cosmic creation. Every planet, moon, and asteroid that exists today was once part of that same violent process. Most matter gets recycled into something new, but some bits get lost forever, floating in the endless dark, like forgotten drafts of worlds that never were. Now, these interstellar vagabonds don't all look alike. Some are icy, carrying frozen gases and carbon compounds. Others are rocky, dense, and weathered. Some may even be metallic, shards of destroyed planet cores. Each one is a time capsule, a piece of evidence from a different solar system's early chaos. But they all share one thing. motion. They never stop moving. Once gravity kicks them out, they coast freely, carried along by their inertia for millions, even billions of years. No star to orbit, no warmth to bask in, just perpetual exile through the coldest reaches of space. If you could follow one of these objects on its journey, it would be a lonely but spectacular trip. It might spend 100,000 years drifting through the outskirts of its birth system, then millions more crossing the gulfs between stars. It might pass through dense nebulae, where starlight filters through clouds like cosmic fog. Occasionally, it might graze the edge of another star's domain, perhaps briefly warmed, maybe even scorched before continuing on. It's a traveler with no destination, guided only by the silent physics that set it free long ago. And they're not easy to spot. These objects are dark, small, and fast, the interstellar equivalent of speeding pebbles. Even our best telescopes can only catch them when they come relatively close, illuminated by sunlight for a short time. Before 2017, we'd never seen one at all. Then Oumuamua zipped by, followed by Borisov, and later 3IATLAS. 3 glimpses in all of human history of what might be billions of travelers roaming the Milky Way. It's like finally seeing a few fireflies in a forest and realizing the woods are alive with them. That discovery reshaped how we see our galaxy. We used to think planetary systems were isolated, each one forming and evolving independently. But now we know they're connected, sharing material across light years. Every interstellar rock is a messenger from another star, carrying a sample of alien chemistry, a whisper of someone else's cosmic story. Some might even carry the basic molecules of life, frozen and preserved for eons, waiting to crash into a new world and deliver their payload. In that sense, these rogues aren't just wanderers. They're couriers, spreading the raw ingredients of existence. Yet, for all their potential, most of them will never be found, never be studied, never even be noticed. They'll keep drifting, invisible to anyone, except the rare civilization, lucky enough to catch one in passing. Each one represents a small tragedy, a piece of a world that almost was, a fragment of planetary potential that got exiled before it could fulfill its destiny. But there's beauty in that, too. Because in their endless wandering, they remind us how vast, how dynamic, and how messy the universe really is. If you could stand on one, assuming you had an unreasonably good spacesuit, you'd see nothing but starlight in every direction. No sun, no horizon, just the infinite glitter of the Milky Way. It would be utterly silent, profoundly still. Yet, that rock would be moving faster than any spacecraft we've ever built, carving its lonely path between the stars. A runaway fragment, carrying the fingerprints of a forgotten system. Maybe even a hint of life's precursors, all because gravity once sneezed. So the next time someone tells you space is empty, remember 3IATLAS and its countless siblings. Space isn't empty. It's alive with motion, littered with stories. Every rogue object is a postcard from somewhere else, stamped by time, addressed to whoever's curious enough to look up and wonder. When 3IATLAS showed up, it didn't exactly make a quiet entrance. It burst onto the scene like a rock star mid-meltdown tour, blindingly bright one moment and in cosmic shambles the next. Telescopes caught sight of it in early 2020, when astronomers from the ATLAS survey, a system designed to spot dangerous near-Earth objects, noticed something streaking through the night sky that didn't fit the usual pattern. At first glance, it looked like just another comet, the kind that politely circles the sun every few decades. But the deeper they looked, the more it behaved like a mystery, wrapped in dust, confusion, and poor structural integrity. The 3I in its name means it was the third confirmed interstellar object humanity has ever seen. That alone makes it a celebrity. The Atlas part, though, is pure irony. This fragile visitor was discovered by an instrument whose full name, the Asteroid Terrestrial Impact Last Alert System, sounds like something that should be accompanied by dramatic music and flashing red lights. Instead of announcing doom, Atlas had stumbled upon a tourist from another star system that was about to dramatically self-destruct for an audience of baffled scientists. At first, excitement rippled through the astronomy world. This could be another Oumuamua, that strange cigar-shaped object that launched 1,000 alien theories. But as more telescopes joined the show, the data started telling a different story. Unlike Oumuamua's shiny, dry surface, 3IATLAS displayed a fuzzy halo, a coma, which meant it was shedding gas and dust like a comet. That was a big clue. Comets form far from stars, where ice can survive. And when those ices heat up near sunlight, they vent gas and dust, creating tails that can stretch for millions of kilometers. So far, so good. A nice, icy interstellar comet, minding its business. But then, almost without warning, 3IATLAS began to fall apart. Astronomers watched its brightness rise sharply, much faster than expected, and then fade. Not fade as in, it's heading away, but fade as in, it's disintegrating into cosmic glitter. Within weeks, telescopes detected multiple fragments where there had been one. In human terms, 3IATLAS didn't just visit. It came apart faster than a flat-pack desk without the manual. The disintegration was both frustrating and fascinating. Normally, comets break apart when they get too close to the sun. The heat turns their frozen interiors into jets of gas that push from the inside, cracking them open like popcorn kernels. But 3IATLAS didn't get that close. It broke up, while it was still hundreds of millions of kilometers away, in a region where other comets glide by just fine. That raised a few cosmic eyebrows. One theory is that it had been weakened long before it arrived. After all, it had spent possibly millions of years drifting through interstellar space, a lonely, radiation-blasted existence that can fracture rock and shatter ice. Cosmic rays, micro-impacts, and the extreme cold could have left its interior brittle, like old pottery left out in the frost. When it finally approached our sun, the slight warming might have been enough to send it over the edge. A gentle cosmic nudge, and the whole thing crumbled. Another idea is that 3IATLAS was born fragile. Comets and small icy bodies are like cosmic snowballs mixed with gravel, loosely packed, held together mostly by frozen gases. If this particular object had an uneven composition, with chunks of volatile ice near the surface, sunlight could have triggered violent outgassing that tore it apart. Imagine a pressure cooker made of dirty ice suddenly finding itself too close to a heater. The result? Instant breakup. Beautiful for astronomers, terrible for the comet's structural integrity. Even in pieces, 3IATLAS had plenty to say. Spectral data hinted that it contained cyanide compounds. Not uncommon in comets, but still a reminder that space is a chemist's playground. It also reflected light in a way consistent with dust grains coated in carbon-rich material, the same type found in ancient meteorites. These clues suggested it was a typical product of a planetary nursery, a mixture of ice, rock, and organic carbon that once orbited a distant star. In other words, a genuine sample of another solar system's building blocks, even if it was now more confetti than comet. Its orbit told an equally dramatic story. The path it followed through our solar system wasn't bound by the sun's gravity. It came in fast, from an angle that made no sense for local comets, and left just as quickly. That hyperbolic trajectory confirmed it came from elsewhere, somewhere out there, maybe hundreds of light years away. A young star once flung it into the void. Since then, it had been traveling alone, untouched, until it stumbled across our corner of space and promptly fell apart from the sheer indignity of existence. For astronomers, that brief appearance was gold. Every observation added a puzzle piece to the story of how other star systems form and evolve. Its breakup, while disappointing, gave insight into how fragile these interstellar objects can be. A reminder that not everything that travels the stars is built to last. Some are more like cosmic mayflies, surviving just long enough to make an entrance before burning out spectacularly. Still, there's something poetic about it. Imagine drifting through the galaxy for millions of years, only to shatter in front of an audience of astonished Earthlings. In that moment, 3IATLAS became both a mystery and a metaphor, a symbol of impermanence on a cosmic scale. It wasn't just a rock passing through, it was a performance, a fragile relic from another sun, playing its final act in the warmth of ours. And when it was gone, it left behind more than dust. It left behind questions about what it was made of, where it came from, and what other fragments like it might still be wandering the void. Each one a message in a bottle from some distant star system, carried across light years, waiting for someone to notice. 3IATLAS may have been short-lived, but it gave us a rare peek into the anatomy of interstellar debris. It reminded us that even the smallest visitors can rewrite what we think we know about the universe. And sometimes the most fleeting things leave the longest echoes. After all, in the grand story of space, even a rock that can't hold itself together still manages to hold our attention. Every planet begins as dust, not poetic dust, not the kind that glitters in sunlight, but the dull, microscopic kind that sticks to everything and refuses to leave. Somewhere in a swirling disk of gas around a young star, that dust bumps into more dust, clings to it, and begins to form something more. It's the cosmic equivalent of breadcrumbs coming together to make a loaf. Slow, accidental, and extremely messy. Over time, those crumbs grow into pebbles, the pebbles into boulders, and the boulders into planetesimals, the planet seeds from which everything else is born. These planetesimals are nature's first draft of planets. They're the universe saying, let's see what happens if we mash this together and wait a few million years. They don't look impressive. Most are irregular, potato-shaped lumps made of rock, ice, or a combination of both, tumbling end over end through the dusty haze of their parent disk. But give them time and a little gravitational ambition, and they start pulling more material in, growing larger, rounder, and more complex. One day, if the conditions are right, they become full-fledged worlds. If not, well, they end up as asteroids, comets, or, in some unfortunate cases, interstellar castaways like 3IATLAS. The process begins in the protoplanetary disk, a sprawling, pancake-shaped cloud of dust and gas surrounding a newborn star. This is the galaxy's version of a construction site. The inner region of the disk is hot, close to the star, where rocky materials like silicates and metals can survive. Further out, temperatures drop low enough for volatile compounds like water and methane to freeze. This creates a boundary called the snow line, and it's one of the most important lines ever drawn by physics. Inside it, rocky planets are born. Beyond it, icy giants and comets take shape. It's a temperature-controlled factory floor for making everything from Mercury to Neptune. But here's the tricky part. Dust grains don't automatically stick together. When they collide at high speed, they tend to bounce off or shatter. Planet formation is like baking cookies in space. Too cold, and the dough never sticks. The grains need just the right conditions to merge. Low-speed collisions, sticky ice coatings, and enough turbulence to keep things mixing without tearing them apart. Scientists call this the meter-size barrier, the awkward stage where particles grow to about a meter in size and then stop, because the forces trying to rip them away outweigh the ones holding them together. It's like trying to build a sandcastle in a wind tunnel. So how do some of them make it past that stage? Gravity, teamwork, and sheer persistence. Clumps of particles that grow slightly larger begin to attract others through their weak gravitational pull. Regions of the disk can also become unstable, creating pressure traps that gather material like a cosmic dustpan. Over time, some planetesimals get lucky, merging into bodies tens or hundreds of kilometers across. Once that happens, the game changes. Gravity becomes their best friend. With enough mass, they can pull in gas and dust more efficiently, growing faster. It's a runaway process. The bigger they get, the faster they grow. But for every planet seed that thrives, countless others fail. Some collide violently and shatter back into dust. Some get nudged too close to the star and evaporate. Others are flung out of the disk entirely by the gravitational tantrums of forming gas giants. Planetary systems, especially in their infancy, are brutal places. You've got thousands of seeds jostling for position, colliding, merging, and competing for resources. Only a handful will ever become planets. The rest are casualties of cosmic evolution, the failed seeds, the lost opportunities, the forgotten prototypes. Those failures, though, are just as important as the successes. They tell us how delicate the process is. Tiny differences in temperature, density, or timing can mean the difference between a rocky world like Earth and a barren lump drifting forever in space. It's a high-stakes experiment played out billions of times across the galaxy, and somehow, out of that chaos, stable worlds emerge, some with oceans, some with atmospheres, and maybe a few with life. What's fascinating is that this process is universal. Every star we observe in its early stages, from tiny red dwarfs to massive blue giants, is surrounded by its own protoplanetary disk. We've seen them with telescopes like ALMA, glowing in radio waves, patterned with dark rings and gaps where new planets are forming. It's like looking at a cosmic petri dish, watching nature mix ingredients and test recipes. Each disk has its own chemistry, its own dynamics, and its own destiny. Some will create rich planetary families. Others might produce only debris, the crumbs left after the baking fails. In a sense, planetesimals are the great gamblers of the universe. Each one is a ticket in the cosmic lottery, a chance at planetary immortality. Most lose, dissolving or colliding before they can grow. But every now and then, one wins big, forming something like Earth or Jupiter, or maybe a habitable world we haven't discovered yet. And even the losers aren't truly wasted. They carry the same materials, water, carbon, minerals, that can later be delivered to young planets via impacts. Earth, for example, owes much of its water to icy planetesimals from beyond the snow line. Even failed seeds can feed success elsewhere. Imagine that on a galactic scale. Trillions of dust grains, billions of collisions, and a few precious survivors that grow into planets capable of oceans, mountains, and weather. It's chaos with purpose, a process so clumsy and violent, yet so astonishingly effective. The universe doesn't need precision. It just needs time and gravity. And somewhere out there, around some distant sun, a new disk is swirling, and the first grains are beginning to stick. Maybe one of them will grow, maybe it won't. But each attempt is another shot at building a world, another round in the endless game of cosmic construction. Planets aren't built overnight. They're assembled by accidents, persistence, and luck. In that light, every world we see, from our own Earth to the gas giants, to the exoplanets orbiting faraway stars, is a survivor of that chaotic process. Every rock, every ocean, every living thing owes its existence to those humble planet seeds that managed, against all odds, to hold themselves together. And that might be the most miraculous thing about the universe. It's not that worlds form, but that any of them manage to stick around long enough to shine. For every planet that proudly circles a star, bathed in light and warmth, there are countless others that never got the chance. These are the forgotten children of the cosmos, the failed planet seeds, the planetary embryos that started to form, began to dream of becoming worlds, and then got booted out before they could even grow an atmosphere. If the universe were a classroom, these are the kids who were told to pack up their things and leave before snack time. And maybe, just maybe, 3IATLAS was one of them. Planet formation, as we've seen, is not a polite, orderly process. It's chaos, with gravity holding the clipboard. Inside those spinning disks of gas and dust around young stars, thousands, maybe millions, of small bodies are jostling for position. They crash, merge, fracture, and reform in an endless ballet of destruction and creation. Every collision changes the odds. Sometimes, two planetesimals gently fuse, starting a new world. Sometimes they smash into each other with the force of 1,000 atomic bombs, turning back into dust and debris. It's cosmic natural selection, but with boulders instead of biology. Now, not all of these early embryos get to stay in the disk long enough to finish the job. Big planets, the ones that form fast and hog the gas, tend to throw their weight around. A newly forming giant like Jupiter can act like the schoolyard bully of its solar system, flinging smaller objects in every direction with gravitational slingshots. Some get tossed inward and incinerated by their star. Others get sent outward, never to return. The unlucky ones are hurled clean out of the system entirely, flung into interstellar space on a one-way ticket to nowhere. That's how a failed seed is born, not through lack of effort, but because gravity plays favorites. Once ejected, there's no coming back. An object like that becomes a rogue embryo, wandering the galactic wilderness without a parent star. No sunlight, no warmth, no stable orbit, just endless night. Whatever potential it had to grow, to host moons, to develop oceans, is frozen forever in that moment of exile. It's like being halfway through building a house when someone takes away your tools and the roof. But even in failure, these seeds are fascinating. They're fossils of the planetary formation process, preserved records of what went right and wrong in some distant solar system. Some might still contain hints of the chemistry that was happening when they were born. Water locked in ice, minerals fused under ancient collisions, maybe even traces of organic molecules. Each one carries a unique fingerprint, a chemical time capsule from a star we may never identify. If you could examine one up close, you might find layers of frozen gases, dust crusts, and rock cores, geological history written in miniature. Some might resemble asteroids, others comets, and a few could be entirely alien in composition, built from elements more abundant or rarer than what we find near our sun. They're unfinished worlds, half sculpted by gravity, then abandoned by fate. And the galaxy is absolutely full of them. Astronomers estimate that for every planet successfully formed, dozens or even hundreds of these failed embryos were ejected along the way. That means there could be trillions of these cosmic orphans wandering between stars. Think about that for a second. Entire populations of half-made worlds drifting through the dark, unseen and unnamed. It's the universe's version of lost potential, a silent reminder that creation and destruction are inseparable. It's possible that 3IATLAS was one of these exiles. Maybe it began as a small clump of rock and ice in the outer regions of a young star system, slowly gathering mass. Maybe it started to build momentum, pulling in more material, beginning to take shape as a proper world in progress. But before it could grow beyond a few kilometers wide, some nearby gas giant flexed its gravitational muscles and sent it flying. One moment, it's basking in the faint glow of its star. The next, it's tumbling into eternal night, its dream of planetary adulthood snuffed out. Imagine being kicked out of your nursery before snack time. Once expelled, it would have drifted between the stars for millions of years, or even longer. Cosmic rays would have bombarded its surface, darkening it to a dull charcoal hue. Ice within might have slowly cracked and refrozen, reshaping its insides. Tiny collisions with interstellar dust could have scarred its exterior, giving it that rugged, ancient look. Over time, it became less a planet in waiting and more a ghost of what might have been, a seed without soil. And yet, that failure might have been part of a larger cosmic pattern. After all, every solar system needs to eject material to balance itself. Those lost embryos may actually play a vital role in stabilizing the survivors. In a strange way, their sacrifice makes planetary order possible. The galaxy's beauty, its shining worlds and habitable oases, exists partly because so many others didn't make it. It's a bittersweet truth. For every Earth that forms, countless other wannabe Earths are scattered into oblivion. But they're not entirely gone. When one of them, like 3IATLAS, drifts into a new system, it becomes a messenger, a piece of one story intersecting with another, a failed planet seed that still has something to teach. So when astronomers spot one passing through our neighborhood, they're not just watching a lump of rock glide by. They're witnessing the fossilized remains of a world that never was. A reminder that even in a universe full of success stories, there are far more that ended in heartbreak. Still, maybe that's what makes these failures beautiful. They're not just debris. They're the unsung beginnings of something greater, the echoes of creation that didn't stick around to see the final act. Their journeys may have ended in darkness, but each one proves that the cosmos is constantly trying, failing, and trying again. Because in the grand experiment of the universe, failure isn't the end. It's part of the process. The prelude to every world that does make it. And sometimes, even the ones that didn't become planets still find their way back into the light, crossing our skies just long enough to remind us how much of creation depends on persistence, chance, and a little bit of chaos. Once 3IATLAS, or any cosmic castaway like it, gets flung into interstellar space, the story shifts from chaotic creation to endless travel. It's the ultimate road trip, except the car is a frozen rock, the scenery is a void, and the journey lasts for millions, maybe billions, of years. No pit stops, no directions, and definitely no music. A billion-year road trip without a playlist or a gas station. When an object leaves the comforting embrace of its parent star, it enters the deep freeze of interstellar space. A place so empty that calling it empty feels like an overstatement. It's not a vacuum in the perfect sense, but close enough that a single cubic meter of it might contain just a handful of stray atoms. Temperatures hover near absolute zero, a kind of permanent deep sleep where molecular motion slows to a near stop. It's the loneliest environment imaginable, and once you're out there, there's no going back. For a world seed like 3IATLAS, the moment of ejection is violent and final. One gravitational misstep, and suddenly it's being hurled into the dark at tens of thousands of kilometers per hour, escaping its star's gravity forever. The heat of its birthplace fades quickly, replaced by cold, so severe that any remaining gases or surface ices freeze solid. What was once an active, dynamic body, colliding, growing, maybe even rotating under the glow of a nearby sun, becomes a silent, frozen relic, adrift in a near-perfect stillness. But stillness doesn't mean safety. The interstellar medium may be thin, but it's not harmless. For millions of years, these wandering objects are bombarded by cosmic rays, high-energy particles accelerated by exploding stars and other cataclysmic events. They slam into the object's surface with enough force to break molecular bonds and rearrange chemistry. Over time, this radiation darkens the surface, turning bright ice into a pitch-black crust. It's a cosmic suntan, if sunlight were made of invisible bullets. This process creates what scientists call a radiation mantle, a layer of altered material that tells the story of eons spent in deep space. Underneath that crust, though, the object may still preserve its original composition. Pristine ices, complex carbon molecules, maybe even traces of organic chemistry that once brewed in its home system. To get to that inner layer, though, you'd have to dig. Not easy when your target has been drifting through the dark for geological ages, hundreds of light years from the nearest coffee shop. And then there's the danger of collisions. Not the cinematic, fiery kind. Space is too empty for that, but slow, quiet impacts with microscopic dust or the occasional wandering pebble. Over millions of years, even tiny grains can leave their mark. Each impact scours the surface, pitting it, eroding it, sometimes embedding new material. Bit by bit, these encounters shape the rock's appearance, leaving it scarred but still intact. Think of it as cosmic exfoliation, the universe's slowest, most brutal skincare routine. Every now and then, our wanderer might pass through a denser region, a molecular cloud where stars are born. There, it might briefly encounter thicker gas, cosmic dust, and the faint glow of ultraviolet light from nearby newborn stars. For a moment, its frozen surface might warm slightly, releasing a wisp of vapor or revealing the glimmer of buried ice before plunging back into the cold. These encounters are fleeting, a few centuries in a billion-year life, but they mark the traveler like milestones on a map. Time, of course, means little out there. There are no days or nights, no orbits to count, no rising suns. Only motion. For something like 3IATLAS, its journey could span not just one galaxy rotation, but many. It could have drifted through spiral arms, past nebulae, near dying stars, maybe even through systems where civilizations rose and fell without ever noticing it. Every few 100 million years, it might pass within a few light years of another star, a near miss that changes its trajectory slightly, bending its path but never capturing it. You could call it eternal exile, but that feels too tragic. In another sense, it's freedom, an unending voyage through the grandest landscape imaginable. Out there, surrounded by starlight and silence, our lonely traveler becomes part of something far bigger, the cosmic migration of matter itself. Every bit of dust, every rock, every icy shard in the galaxy is part of that motion, circulating endlessly, recycled across eons into new stars and planets. In that way, even drifting alone, it still participates in the great galactic conversation. If you were somehow to stand on the surface of such an object, assuming your body could survive the vacuum and cold, the view would be breathtaking. You'd see stars brighter and sharper than you've ever seen them from Earth, because there's no atmosphere to blur the light. You'd be able to see the Milky Way as a glowing river stretching across the sky, a reminder of the galaxy you're floating through. But there would be no sound, no wind, no horizon. Just infinite stillness. It's a place beyond time. The ice beneath your feet might be older than Earth, older than the sun, a relic from the earliest days of cosmic chemistry. Every molecule on that surface has been shaped by the silent persistence of radiation and gravity, molded not by hands or tools, but by the patient, indifferent passage of time. And eventually, maybe after billions of years, something extraordinary might happen. One of these travelers, maybe 3IATLAS, maybe another, drifts close enough to a new star system to be pulled in again. After an eternity of cold solitude, it finds warmth. It flares briefly, shedding dust and ice, announcing its arrival before vanishing once more. a flicker of life in an endless journey. That's what 3IATLAS was when we saw it. Not the start of a story, but the middle of one that began long before us and will continue long after we're gone. Its journey through interstellar space wasn't aimless. It was the natural fate of matter caught in motion. It may not have had a destination, a playlist, or a gas station, but it carried with it the quiet dignity of endurance. And maybe that's enough. Because in the vast stillness of the galaxy, even the loneliest traveler tells us something profound, that no matter how far you drift, you're still part of the story the universe is telling. When astronomers first spotted 3IATLAS streaking into the solar system, they expected it to behave like a comet on a grand interstellar adventure. Maybe flare up a bit as it neared the sun, throw off some dust, and then sail gracefully back into the dark. Instead, it went full drama queen. Within weeks of discovery, it began to disintegrate, fading and fragmenting until nothing solid remained. One moment, it was the guest of honor in the cosmic spotlight. The next, it was space dust. The question that lingers is, why? Why would a chunk of rock and ice that survived millions, possibly billions, of years adrift between stars, suddenly fall apart the instant it wandered into our neighborhood? The short answer is that space is brutal. Even rocks can't keep it together. Let's start with what we know. When 3IATLAS entered the inner solar system, it began warming up for the first time in eons. Out in interstellar space, it would have been colder than anything we can imagine, just a few degrees above absolute zero. But as it approached the sun, temperatures began to rise, and all that ancient ice buried beneath its surface started to stir. On Earth, that might sound cozy. In space, it's a recipe for chaos. Comets, which are made of similar materials, go through a process called sublimation when they get close to a star. Ice doesn't melt. It vaporizes directly into gas, forming jets that spurt out from the surface like tiny geysers. These jets can propel dust and fragments away, giving comets their characteristic tails. Normally, that's fine, but if those jets erupt unevenly or deep within the structure, they can create internal pressure. And if the comet's body isn't strong enough to handle it, boom! Instant fragmentation. For 3IATLAS, this might have been the final straw. Its internal structure was probably fragile. A loose clump of dust and frozen gases held together by weak bonds. You can think of it as a cosmic snowball that had been sitting in a freezer for a few billion years. When it finally came close enough to the sun, the outer layers heated first, while the inside was still frozen solid. That temperature difference created thermal stress, like heating a glass marble with a blowtorch. Cracks formed, pressure built up, and before long, the whole thing fractured apart, like a brittle sculpture exposed to too much heat. But there's more to it than just temperature. After millions of years exposed to cosmic radiation, 3IATLAS's materials had probably become chemically unstable. Radiation can rearrange molecules, turning once flexible ices into rigid, glassy substances. Imagine freezing a sponge and then expecting it to flex. It just doesn't. When sunlight hit those frozen chemicals for the first time in ages, they reacted violently, releasing trapped gases that expanded faster than the structure could handle. The result? A slow-motion explosion, disguised as a graceful disintegration. There's also the issue of spin. As 3IATLAS released gas jets, it may have started to rotate faster, the same way a figure skater speeds up by pulling in their arms. This effect, called torque from outgassing, can destabilize small bodies. If the spin becomes too fast, the centrifugal force literally tears them apart. Think of it as a self-induced spin cycle of doom. One wrong puff of gas, and suddenly your fragile interstellar traveler is flinging itself into pieces at thousands of kilometers per hour. Astronomers watching 3IATLAS noticed that it brightened dramatically before breaking up, a sign that sunlight was triggering a burst of activity. It didn't just crumble quietly, it flared. The sudden increase in brightness meant it was venting more gas and dust than before, possibly exposing new ice layers as it fractured. It was like watching a slow explosion unfold over days instead of seconds. The bright show was beautiful, but it also told us that the comet's insides were tearing themselves apart. One theory suggests that 3IATLAS wasn't a single solid object to begin with, but rather a cluster of smaller pieces loosely held together. This rubble pile structure is common among comets and asteroids. Instead of being one monolithic chunk, they're more like cosmic trail mix, a bunch of fragments stuck together by mutual gravity and frozen gases. When one part gives way, the rest quickly follows. The disintegration we saw could have been the unraveling of a structure that was never stable in the first place. There's a kind of melancholy beauty to that. Here was an object that had survived unimaginable distances, countless impacts, and the emptiness of deep space, only to meet its end because it got a little too warm. You could say 3IATLAS died of success. It finally got noticed, and the attention proved fatal. But even in its demise, it gave scientists invaluable clues. By studying the fragments and their light signatures, astronomers could infer what the object was made of: mixtures of volatile ices, organic compounds, and silicate dust. That tells us something profound about its birthplace. Somewhere, long ago, in the disk around a distant star, those materials condensed and froze together. Its destruction became a final act of revelation, exposing its internal chemistry for all to see. In the bigger picture, 3IATLAS's fate isn't unusual. It's practically tradition for comets and interstellar visitors. Fragility is the norm in the cosmos. The same forces that build planets also destroy the smaller bodies that never quite made it. Gravity, heat, and radiation don't play favorites. They shape and unmake with equal enthusiasm. 3IATLAS just happened to remind us how fine the line is between survival and dissolution. in the harsh theatre of space. So, why did 3IATLAS break apart? Because it was old. Because it was fragile. Because the sun doesn't do gentle. It had survived ejection, exile, and the endless cold, but it couldn't withstand warmth. Its final act was to burst into brilliance, a cosmic firework marking the end of a journey measured in light years. It's easy to anthropomorphize and say it gave up, but maybe it didn't. Maybe disintegration was its destiny, to scatter fragments across our solar system, leaving behind traces of alien chemistry for us to study. In that sense, it didn't fail at all. It just ended the way all travelers eventually do, by leaving a story in its wake. 3IATLAS didn't just break apart. It shared itself with the universe. And for a rock that couldn't keep it together, that's not a bad legacy. Somewhere between the words rock and life, there's an uncomfortable silence. A kind of existential pause where science wonders if the two might overlap more often than we think. When 3IATLAS tumbled into our solar system, shattered, and slipped back into the void, it left behind a curious question. Could it have carried the ingredients of life? Not life as in tiny aliens waving from a porthole, but life in its most basic chemical form, the seeds of possibility. It's a question wrapped in one of science's boldest ideas. Panspermia, the notion that life, or at least the ingredients for it, can travel between worlds. Imagine it as the universe's ultimate delivery service. Bits of organic matter hitching rides on comets, asteroids, and yes, maybe even interstellar objects like 3IATLAS, spreading across star systems like cosmic dandelion seeds. If space ever had a fertility clinic, this rock was probably in the waiting room. To even consider that, we first have to understand what life's ingredients means. On Earth, life is built on a foundation of simple chemistry: carbon, hydrogen, oxygen, nitrogen, and a few other elements that enjoy forming complicated relationships. These atoms come together to form organic molecules: amino acids, sugars, and nucleobases, the building blocks of proteins and DNA. We know these molecules aren't unique to Earth because we've found them everywhere. Meteorites that have landed here carry them. Comets studied by spacecraft contain them. Even the icy moons of Jupiter and Saturn hide them beneath their frozen crusts. So, if these molecules can form in our solar system, there's no reason they couldn't form in others. In fact, interstellar space itself, that seemingly barren gulf between stars, is rich with them. Radio telescopes have detected complex organic molecules floating in dark nebulae, where dust and gas mingle under ultraviolet light. It turns out that, given enough carbon and time, the universe just can't help but make organic chemistry. Life's recipe seems to be written everywhere, just waiting for a chance to bake. Now, picture 3IATLAS at its birth, long before its ill-fated visit to our solar system. Somewhere around another star, in a cold outer region of a young disk, ices condensed around dust grains. Those ices weren't pure. They were laced with simple organic molecules: methane, methanol, formaldehyde, and other tongue twisters that make chemists grin. As these molecules were bombarded by radiation, they combined into more complex forms. Layer after layer, chemistry built itself up, freezing into the body of what would eventually become 3IATLAS. By the time it was ejected into interstellar space, it wasn't just a rock. It was a chemical archive, a frozen library of organic history. Of course, there's a big leap between having the ingredients for life and actually being alive. No one's suggesting 3IATLAS was harboring microbes in its core, tucked in for a billion-year nap. The temperatures out there are far too low, the radiation too intense, the environment too sterile. But the ingredients, those could absolutely survive. Frozen in deep space, organic molecules can last for millions or even billions of years without breaking down. The cold acts as a preservative, locking them in place until, and here's the fun part, they find a new home. Imagine that sometime in the distant past, 3IATLAS passed through a planetary system and a tiny fragment broke off, drawn toward a warm, young world covered in oceans. That fragment crashes down, melts, and releases its cargo of complex carbon chemistry into a fertile soup. Maybe nothing happens. Or maybe, over time, those molecules spark something extraordinary, a chain reaction that leads to self-replicating chemistry, and eventually, life. It's a cosmic what-if that gives panspermia its allure. Not that life came from space, but that the potential for it might drift freely between stars. The idea isn't new. The great thinkers of centuries past, from the philosopher Anaxagoras to scientists like Svante Arrhenius, wondered if life might be a universal phenomenon scattered like spores across the cosmos. Modern astrobiology just gives that idea better tools. We know that microbes on Earth can survive incredible extremes: boiling heat, crushing pressure, radiation that would fry electronics. Some bacteria even hibernate in space-like conditions for years, waiting for a better environment. If life can endure that here, it's not unreasonable to imagine it doing the same elsewhere, even hitching rides on rocks thrown out by impacts or ejections. Still, 3IATLAS is more likely to have been a potential carrier, not a literal one. Its icy body might have been full of organic molecules, but not organized biology. It was a prelude, not the symphony. The chemicals frozen within it were the kind that, under the right conditions, warmth, liquid water, a stable environment, could form the complex chains that eventually wiggle and divide. If you think of life as fire, then 3IATLAS carried the kindling. It just never found the spark. What makes that fascinating is the universality of it. Everywhere we look, we find the same chemical patterns repeating: carbon combining with hydrogen, nitrogen binding with oxygen, complex molecules forming spontaneously. Life, it seems, isn't a rare cosmic accident. It's chemistry that got lucky. And if that's true, then every interstellar rock like 3IATLAS isn't just a fragment of some lost planet. It's part of a galactic experiment in possibility. Even its disintegration, tragic as it seemed, could have helped spread those ingredients. When it broke apart near the sun, tiny dust grains containing ancient carbon compounds scattered into the solar wind. Some may still be drifting through our system, eventually falling into planets, moons, or even Earth's atmosphere. Maybe a few molecules from a dead planet seed are, right now, floating quietly down through our skies, unnoticed, waiting to join new chemistry. So was 3IATLAS alive? No, at least not in any way we'd recognize. But was it part of the process that makes life possible? Absolutely. It carried within it the same materials that built oceans and DNA and thoughts. It was a courier of cosmic raw materials, a silent participant in the grand chain that connects stars, planets, and eventually minds wondering where they came from. It's oddly poetic, a fragment of a failed world carrying the possibility of others. A frozen messenger that spent eons in the dark, and in the briefest flash of time, shared its secrets before fading away. It may not have been alive, but it was life-adjacent, and that's close enough to stir the imagination. After all, in a universe that never stops recycling its ingredients, who's to say that 3IATLAS didn't, in some distant future, help something else come alive? When you zoom out far enough, our galaxy stops, looking like a serene spiral of light, and starts to resemble what it really is: a massive, chaotic workshop. Every glowing arm of the Milky Way is a conveyor belt of creation, an assembly line where stars are born, live fast, die dramatically, and scatter the ingredients for the next generation. It's not a quiet factory either. It's loud, messy, and wonderfully inefficient. Yet, somehow, out of all that cosmic commotion, you get planets, moons, and occasionally a small blue world that invents coffee and existential dread. You could think of the Milky Way as the universe's great nursery, one that's been in business for over 13 billion years. Inside this nursery, stars form in clusters from cold clouds of hydrogen gas. As those stars ignite, their light and radiation begin sculpting the material around them, creating cavities, shocks, and jets. This is where the magic begins. Those same regions of leftover dust and gas are the raw ingredients for planetary systems. Every star born in a stellar nursery comes with its own starter kit of cosmic material, ready to be molded into worlds. But it's not a smooth process. Imagine a galactic kindergarten where billions of toddlers are all trying to build sandcastles in the same sandbox. Collisions, tantrums, and accidental demolitions are the rule, not the exception. For every planet that manages to form and hold together, countless others fail mid-construction. The galaxy isn't a neatly organized factory line. It's more like an endless art project that keeps spilling glitter everywhere. Astronomers estimate that our Milky Way alone contains hundreds of billions of stars, and most of them likely have planets. That means there are trillions of worlds out there: gas giants, rocky orbs, frozen spheres, molten infernos. But not all of them were success stories. Many never reached completion. Some got smashed apart by early collisions. Others were swallowed by their stars or thrown into interstellar exile. Planet making is less like crafting a sculpture and more like surviving a demolition derby with gravity as the referee. And yet, somehow, it works. Just enough to matter. The very dust and debris left behind from failed attempts don't go to waste. Every explosion, every shattered world becomes new raw material for future generations. Supernovae, those dramatic deaths of massive stars, spew heavy elements like carbon, oxygen, silicon, and iron into space. Those elements later mix into clouds that form new stars and planets. In a very literal sense, the galaxy recycles itself. The iron in your blood, the oxygen in your lungs, the silicon in your phone, all forged in the heart of dead stars. It's the most beautiful kind of cosmic reuse program imaginable. The galaxy's nurseries, places like the Orion Nebula or the Carina Nebula, are where we see this cycle in action. Through telescopes, they look like paintings. Vast curtains of glowing gas, lit by the ultraviolet radiation of newborn stars. Inside those curtains, millions of tiny clumps of matter are spinning, coalescing, and forming disks. In each of those disks, thousands of planet seeds are competing for survival. A few will grow up to be planets. Most will be ground back into dust. And that's the quiet, relentless rhythm of galactic life. Creation through destruction, order through chaos. Our own solar system emerged from one of these nurseries about 4.5 billion years ago. A cloud of gas collapsed under gravity, spun into a disk, and from that chaos came the sun and its retinue of planets. But here's the thing. It almost didn't happen. The odds of creating a stable, life-bearing world like Earth are absurdly low. Every step in the process, the right kind of star, the right orbit, the right chemical mix, the right amount of time, has to line up perfectly. The universe doesn't make many Earths. Statistically speaking, we're the weird kid in class who actually finished the science project. And that perspective changes everything. When we look up at the night sky, we're not seeing distant pinpoints of light. We're looking at other nurseries, other experiments, other attempts. Each star might have its own set of planets, some half-formed, some thriving, some long gone. Somewhere out there, a system might be in the middle of its chaotic youth, its planet seeds colliding and growing just like ours once did. Somewhere else, a planet might be cooling from a cataclysmic impact, waiting for oceans to condense. And in countless other places, planet embryos like 3IATLAS may already have been cast out, wandering the spaces between suns. That's what makes galaxies so astonishing. They're not static. They're living ecosystems on a cosmic scale, always changing, always producing new possibilities. When you look at the Milky Way, You're seeing an unending experiment in creation, where the raw materials of stars are constantly recycled into new forms. Some of those forms will glow with light. Others, like our Earth, will glow with life. But even as we marvel at that abundance, it's worth remembering how rare our particular circumstances are. Out of billions of seeds scattered through the galaxy, only a few grow into stable, life-supporting worlds. The rest become comets, asteroids, or orphaned rocks like 3IATLAS. A reminder that for every success story, there are countless near misses. The universe is generous with its experiments, but it's not sentimental about the results. Still, there's something comforting about that vast, messy cycle. We are, quite literally, the children of failed stars and shattered worlds. Our atoms were once part of other stories, other suns, other planets, other attempts. The galaxy doesn't create perfection, it creates potential. And sometimes, potential is enough. So when we think of Earth orbiting quietly around its middle-aged star, we should recognize it for what it is. A cosmic fluke that beat the odds. A tiny oasis in a galactic nursery still full of noise, dust, and dreams. Out of billions of experiments, this one managed to hold together long enough to look back at the universe and ask how it all began. And maybe that's the point of the great cosmic nursery. Not that it makes perfect worlds, but that it keeps trying. Again and again, it throws seeds into the dark, hoping that somewhere, someday, one of them will wake up and start wondering where it came from. Let's take a moment to imagine the universe with one small edit. In this version of reality, 3IATLAS didn't get flung out of its home system. It didn't wander between stars, and it didn't break apart under the harsh sunlight of our neighborhood. Instead, it stayed put, gathered more dust, and became something bigger, something alive in the planetary sense. In this timeline, 3IATLAS wasn't a failed seed. It was a world that made it. So what would that world have looked like? To answer that, we have to rewind to its possible birthplace. We don't know which star system it came from, but based on its composition, icy, volatile, fragile, it likely formed far from its parent star, out beyond the so-called snow line. That's the region where temperatures are low enough for water, methane, and ammonia to freeze solid. If it had stayed there and kept accreting material, it might have become something like an icy planet, or perhaps a small gas giant. Think of Neptune's distant cousin, orbiting a dim red sun. A red dwarf star would have been a fitting home. These tiny stars make up the majority of the galaxy's population. They burn cool and slow, living for trillions of years. Cosmic tortoises compared to the fleeting flames of bigger stars. Around such a star, our hypothetical Atlas world could have found stability. It would have been bathed not in golden light, but in a faint, perpetual dusk, the kind of twilight that never quite ends. Its skies might glow in deep crimson, and its horizon could shimmer with frozen plains under a salmon-colored sun. If it formed large enough, say, with a solid core wrapped in thick layers of ice and gas, it could have built an atmosphere. Perhaps mostly hydrogen and helium, with traces of methane giving it a bluish hue. From space, it might have looked like a miniature Neptune, softly glowing in the dim light of its parent star. Winds would howl across its upper layers, sculpting bands and storms, each one powered by the slow leak of heat from its interior. Give it a little luck, and it could have been out there hosting alien weather reports. Today's forecast: eternal twilight with a 100-kilometer-per-hour breeze and a high chance of methane snow. But let's say it took a slightly different evolutionary path. One where it formed a bit closer in, near the inner edge of the snow line. There, the mix of rock and ice would shift. Instead of becoming a gas giant, it might have turned into an ocean world, a planet entirely covered in water, deeper than anything Earth could imagine. Beneath the surface, high pressures would compress ice into exotic crystalline forms. Ice that's solid, yet burns blue like sapphire. Its oceans might churn with ammonia-rich water, a strange chemical soup where organic molecules could mingle and react in slow, alien chemistry. In that world's distant atmosphere, clouds could form not from water vapor, but from hydrocarbons, orange and gold, painting the sky with perpetual storms. Lightning might flash above seas of methane. If it were large enough to maintain internal heat, geysers could erupt from its crust, venting plumes of vapor into the sky. The planet's day might last weeks, its year centuries. Seasons would be gentle, almost meditative, the slow turning of a world with more time than hours to change its mind. And maybe, just maybe, something would begin to stir in those oceans. It wouldn't be life as we know it. No fish, no forests, but chemistry edging toward biology. Complex molecules forming chains, patterns, reactions that self-sustain. It could take millions of years, or billions. But the conditions would be right. Warmth from below, protection from radiation, and a steady supply of raw materials from above. Life doesn't need sunlight, just stability and curiosity. If 3IATLAS had gone down that road, its story would have been long and quiet. It might never have developed intelligent life or even multicellular organisms. But it could have harbored ecosystems of slow, chemical persistence. Alien microbes drifting in its ammonia oceans, whispering to one another in molecular exchanges. From space, it would look calm. But beneath its clouds, tiny, unseen dramas would play out. Survival, evolution, the first hints of awareness. Of course, its fate would depend heavily on its star. Red dwarfs, for all their longevity, can be temperamental in their youth. They flare violently, blasting nearby worlds with radiation. If our hypothetical planet formed too close, it might have lost its atmosphere early, stripped bare before life had a chance. But if it survived that fiery adolescence and settled into a stable orbit, it could thrive for trillions of years. While our sun one day swells and dies, that distant world would still be orbiting quietly, its story ongoing while ours fades to dust. The fascinating thing about this thought experiment is that there's nothing implausible about it. We already know of exoplanets that fit the mold. Ocean worlds around red dwarfs, ice giants orbiting faint suns, mini Neptunes cloaked in hydrogen skies. Some of them might even be what 3IATLAS could have been. In that sense, the galaxy is full of alternate versions of our lonely traveler, cousins that didn't get ejected, siblings that found stability instead of exile. And there's something hauntingly beautiful in that idea. Somewhere out there, under the faint glow of another sun, a planet that could have been 3IATLAS might be spinning peacefully, its clouds drifting, its seas frozen and thawing in cycles older than life on Earth. Perhaps no one will ever see it, but it exists nonetheless. A success story in a universe that rarely hands out happy endings. If things had gone just a little differently, a nudge less from gravity, a collision avoided, 3IATLAS could have been one of those worlds. A place with weather, with chemistry, maybe even with the slow heartbeat of something almost alive. Instead, it passed through our sky as dust and light, a reminder that every world begins with a possibility. In another version of the universe, we'd be pointing our telescopes at that faraway world, not watching it fall apart, but watching it shine. And maybe, just maybe, somewhere out there, in the galaxy's endless sprawl, a planet very much like that still does, carrying on the dream that 3IATLAS never got to finish. If the universe had mail, it would be the slowest postal service imaginable. No trucks, no sorting centers, no overnight express, just rocks. Trillions of tiny couriers drifting through space, carrying microscopic packages of carbon, water, and the potential for life. Delivery time? Somewhere between now and the next Big Bang. Galactic delivery service. Guaranteed arrival sometime between now and the next Big Bang. The idea isn't just poetic, it's plausible. Those rogue objects we've been talking about, like 3IATLAS, may not just be failures in the planetary production line. They could be messengers, ferrying material from one solar system to another. Every time a young star system sneezes, through collisions, gravitational scuffles, or stellar winds, it ejects countless fragments into the void. Some of those fragments, rich in organic molecules and frozen ices, might one day pass close enough to another star to be captured or collide with a planet. And just like that, the ingredients for life, or at least the raw chemistry that can lead to it, get shipped across light years. The universe might not do email, but it's been running interstellar snail mail for billions of years. Let's picture how this cosmic postal service works. A star is born in a nebula, surrounded by a swirling disk of dust and gas. Planets begin to form, but it's a messy process. Collisions fling debris everywhere, comets get booted to the outer reaches, and occasionally, gravity sends an unlucky fragment hurtling into interstellar space. Once ejected, that object becomes a carrier, sealed in the cold vacuum, where everything slows down to near timelessness. Inside, complex molecules, amino acids, alcohols, hydrocarbons, are locked in place, preserved perfectly for eons. Eventually, some of those frozen couriers drift close to another system. The odds are low, but not zero. And in a galaxy with hundreds of billions of stars, even rare events happen frequently somewhere. If one of those wanderers brushes near a planet's gravity well, it can be captured or crash headlong into the surface. When it does, it delivers its precious cargo, molecules that once formed under another sun. In that moment, one planetary chemistry meets another. It's like the cosmos shaking hands with itself. This exchange of material isn't just theoretical. Scientists have long suspected that our own solar system sends and receives such packages. We already know that rocks can travel between planets within a single system. Pieces of Mars, for instance, have been found here on Earth. When big impacts occur, they can fling debris into space, some of which escapes entirely. Over time, those fragments drift, orbit, and sometimes get caught by another world. The leap from interplanetary to interstellar isn't that big. It just takes more time and a lucky trajectory. So perhaps 3IATLAS and its interstellar siblings aren't mere wanderers, but participants in a grand galactic circulation. A rock that formed around a star in one arm of the Milky Way could, over billions of years, end up depositing its molecules near another, and then another. Slowly, patiently, like pollen in a cosmic breeze, the ingredients of life spread across the galaxy. It's an elegant thought, a form of natural panspermia, not driven by intent, but by physics itself. The universe doesn't need spaceships to share its secrets. It uses momentum and time. Every ejected comet, every shattered planet seed becomes a courier. Their journeys span epochs, but their mission is simple: to move matter from where it was to where it isn't. Now, whether that material can actually survive the trip and still spark life is another question. Space is not exactly gentle. Between cosmic radiation, micrometeor impacts, and deep cold, even tough organic molecules face a hard road. But experiments on Earth have shown that some simple compounds, amino acids, sugars, and even microbes, can endure shocking extremes. They can survive freezing, vacuum, radiation, and violent re-entry through an atmosphere. Life, it seems, comes with an absurdly high tolerance for nonsense. So, if a fragment like 3IATLAS carried organic material, or even dormant microbes, could they have survived its million-year exile between stars? Possibly. And if so, what happens when it finally collides with a warm, wet planet? A few molecules dissolve, reactions begin, chemistry stirs, and suddenly the cosmic postman has delivered something priceless, the spark of potential. This idea turns the galaxy into one vast ecosystem of exchange. Stars aren't isolated islands. They're neighborhoods constantly trading dust, ice, and organics. The Milky Way, in this view, is less like a collection of separate solar systems and more like a massive, interconnected network, a galactic chemistry set where ingredients circulate endlessly, recombining into new worlds and, perhaps, new forms of life. If that's true, then no planet's story is entirely its own. The carbon in our bodies might have been cooked in another star. The water in our oceans might have started as ice around an alien sun. And the very molecules that led to life could have traveled through interstellar space for ages before arriving here. Earth might just be one link in a chain of cosmic delivery, a stop along the route of some long-forgotten interstellar courier who dropped off its cargo and kept going. It's funny to think of it that way. Evolution and chemistry, powered not just by local luck, but by galactic cooperation. Life might not have emerged in isolation, but as the byproduct of a universe that never stops sharing. Every impact, every explosion, every wandering object is a message written in atoms, saying, "Here, take this. Maybe it'll grow into something amazing." So perhaps 3IATLAS wasn't just a failed planet. Maybe it was a delivery truck that didn't make it to its destination. Its icy cargo spilled early, scattered into sunlight, and burned away before we could open the package. But that doesn't mean the service is over. Somewhere out there, other fragments are still on their routes, carrying their invisible messages, slow but steady, across the galaxy. And who knows? Maybe that's how the universe evolves life. Not through single miracles, but through billions of small deliveries, each one nudging the chemistry of a world closer to consciousness. After all, it's not about how fast the mail gets there. It's about the fact that, one way or another, it does. In human terms, failure is something to be avoided, an unwelcome guest that shows up just when you thought you had everything under control. But in the universe's playbook, failure isn't a bug. It's the system working exactly as intended. Space doesn't do perfection. It does iteration, creation by repetition, trial and spectacular error. And if 3IATLAS could tell its story, it would probably shrug and say, "Hey, I was just one of the test runs." Because that's the secret most cosmic processes share. Almost everything fails. Most stars never host stable planetary systems. Most planet seeds never grow past the size of a mountain. Most attempts at world building end in collision, evaporation, or exile. Even in space, success rates are terrible. But the universe doesn't stop trying. That's the real lesson of 3IATLAS. Not its fragility or its brief, glittering demise, but what that failure represents about the nature of creation itself. The universe is not an artist sculpting a masterpiece with careful precision. It's more like a restless painter, splattering matter across a cosmic canvas and seeing what sticks. The miracle isn't that so many seeds fail, it's that any of them succeed at all. Planet formation, as we've seen, is chaos disguised as progress. Disks of dust swirl, particles collide, and gravity tries to make sense of the mess. It's a process where failure isn't just expected, it's necessary. Every collision that goes wrong creates new material for another attempt. Every shattered fragment becomes the raw ingredient for something else. Even a disintegrating interstellar wanderer like 3IATLAS might one day contribute its remains to another world. In a cosmos that recycles everything, even failure is productive. This kind of resilience, this cosmic persistence, is woven into the structure of reality. Look at how stars are born. A cloud collapses under gravity, ignites and shines for millions or billions of years. But only some clouds reach that point. Most dissipate before they ever form a star. Yet, the universe keeps making them anyway. It's as if creation has no off switch. It doesn't care about the odds, it just keeps rolling the dice. That's why the story of 3IATLAS is strangely uplifting. Here was a fragment that didn't make it, a planet that never was, a traveler that didn't survive its encounter with our sun. But even in that failure, it offered us something of immense value: knowledge. For astronomers, it became a data point in understanding how fragile interstellar bodies behave. For storytellers and scientists alike, it became a symbol of endurance, proof that even a rock drifting for millions of years can still teach us something before it disappears. In that sense, the universe's failures aren't wasted. They're experiments. Every shattered world, every broken comet, every dark cloud that never formed a star, all of them are part of an endless feedback loop, refining the physics of creation. It's a cosmic version of evolution. Systems that don't work are discarded, and the ones that do become templates for more. The fact that Earth exists at all, orbiting stably around a friendly sun, is the result of billions of these failed prototypes. But there's another side to this lesson, a philosophical one. When we call something a failure, we're assuming it had a purpose it didn't fulfill. Yet, in cosmic terms, purpose is retrospective. Maybe 3IATLAS wasn't supposed to become a planet. Maybe its real role was to wander, to break apart, to scatter dust into a system that would one day use it. The hydrogen in our water, the carbon in our cells, the metals in our bones, all of it was once part of something that failed in the traditional sense. Stars exploded, worlds collided, and debris rained across space. Without those failures, we wouldn't exist. So perhaps failure isn't the opposite of success in the universe. It's the fuel for it. A galaxy where nothing ever broke apart would be sterile, locked in stasis. It's the constant collapse and renewal, the falling and rebuilding that keeps everything alive in the cosmic sense. 3IATLAS didn't get its own orbit, but its story adds to a collective understanding of how worlds are built and destroyed. It's a reminder that creation often requires destruction first. Even in our search for life beyond Earth, we can see this principle at work. Most planets we've discovered are inhospitable, too hot, too cold, too toxic, too turbulent. They're failures by our life-centric standards. Yet, their existence gives us context. They define the narrow window in which life can exist, teaching us where the line between sterility and fertility lies. Without the failures, we wouldn't recognize the rare conditions that make worlds like ours possible. It's easy to romanticize the universe as a flawless machine, but it's closer to a learning organism. It experiments relentlessly, unafraid of mistakes. And in that, there's something profoundly human. We, too, are products of billions of years of trial and error, biological, geological, and personal. Our species wouldn't exist without countless evolutionary dead ends, just as our planet wouldn't exist without countless failed planet seeds. Every success is built on the rubble of what came before. Maybe that's why stories like 3IATLAS resonate with us. They mirror our own pattern, trying, breaking, rebuilding, trying again. The rock may not have known it, but its journey through space, long, lonely, and brief in its finale, is a perfect metaphor for persistence. It failed to become a planet, yes, but in doing so, it succeeded in showing us how failure fits into the architecture of the cosmos. So, if we could send a message back to 3IATLAS, it might be this: you didn't fail, you just didn't finish. And maybe that's the same thing the universe says to every world that never makes it. A quiet assurance that even unfulfilled potential has purpose. Because if there's one thing the stars have proven again and again, it's that creation doesn't quit. Matter breaks apart, collapses, reforms, and tries again. From dust to dust once more, the process never ends. And through it all, one truth stands steady, carved into the heart of existence itself. Failure isn't the end of the story. It's how the story keeps going. Every time something like 3IATLAS swings through our solar system, it's a race against time. The universe doesn't wait for anyone, not even scientists with expensive telescopes and a strong coffee addiction. These interstellar visitors appear suddenly, flash across the sky for a few weeks, and then vanish forever, leaving behind only data, confusion, and a trail of cosmic breadcrumbs. Catching one is like spotting a firefly in a thunderstorm. Studying it? That's even harder. Astronomers call it transient science, the study of things that don't stay still long enough to study properly. It's a bit like doing detective work on a suspect who's already left the crime scene. All you've got is a few footprints, some blurry photos, and the faint smell of burnt molecules in the air. Yet, somehow, humanity has become remarkably good at turning those clues into entire stories about objects billions of years old. When 3IATLAS was first discovered, it was just a blip, a moving dot among countless others captured by automated sky surveys. The ATLAS system, short for Asteroid Terrestrial Impact Last Alert System scans the sky every night, looking for anything that shifts position from one image to the next. Most of what it finds are routine: asteroids, comets, bits of space junk. But occasionally, something stands out, moving too fast, too steep, too strangely. That's when the alarms go off, and the world's astronomers collectively drop their coffee mugs. Once a new object is flagged, telescopes across the globe, and even in orbit, are called into action. They pivot, align, and lock on. The clock is ticking. Because interstellar visitors don't linger, every night matters. Every photon of light counts. Teams in Hawaii, Chile, Spain, and beyond start taking measurements: brightness, position, movement. It's an international relay race conducted entirely in silence across thousands of miles, with the stars as the only spectators. But here's the challenge. 3IATLAS was faint, really faint. By the time it was noticed, it was already starting to crumble. You can't just zoom in like in the movies. What astronomers actually do is collect its light, tiny trickles of it, through the filters of their telescopes. That light, stretched and spread out into a spectrum, becomes the key. The lines and dips in that spectrum reveal what the object is made of. Every element, from carbon to oxygen to cyanide, leaves its signature behind, like fingerprints under ultraviolet light. The process is meticulous. Observers stay awake through long, cold nights, watching screens that flicker with faint traces of starlight. Computers record numbers, not pictures, arrays of brightness and wavelength. Later, those numbers are turned into graphs, peaks and valleys that correspond to molecules and minerals. It's less glamorous than a telescope commercial makes it look. But in those squiggly lines lies the entire story of an interstellar object's birth and death. Then comes the orbit modeling. Using the object's changing position across the sky, scientists calculate its path backward and forward in time. For 3IATLAS, those models quickly revealed something extraordinary. It wasn't orbiting the sun in a closed loop. Its trajectory was hyperbolic, meaning it came from beyond our solar system and would never return. In other words, it was passing through, just visiting. That single mathematical realization, derived from a few dots on a graph, transformed a faint speck of light into a message from another star. But even with all this data, there are limits. By the time astronomers got a handle on what 3IATLAS was, it was already breaking apart. Its brightness changed daily, its fragments scattering, its composition obscured by clouds of dust. Imagine trying to reconstruct a sculpture from the confetti it exploded into. Yet, even that disintegration provided data. The way the fragments moved told scientists about its density, its structure, even how fragile it had become after eons in space. This kind of investigation doesn't end when the object disappears. The data lives on, in observatories, in servers, in the minds of researchers. Teams spend months, even years refining their models, arguing over the chemistry, comparing it to known comets and asteroids. They recreate the object virtually, simulating how it would have looked, how it might have formed, and how it met its end. It's forensic astronomy at its finest, piecing together the life of a visitor we'll never see again. And there's a certain poetry to that. Humanity, a species that still occasionally misplaces its car keys, has developed the ability to detect a fragment of rock traveling between stars. We can measure its speed, analyze its chemistry, and determine where it's been, all without ever touching it. It's as if the universe leaves us postcards in light, and we've learned to read the handwriting. The people behind this work are part detective, part artist, and part insomniac. They operate telescopes from mountaintops above the clouds, in air so thin you can feel your heartbeat. Others sit in labs, surrounded by computers and equations, trying to make sense of the faintest glimmers in the data. It's painstaking, often thankless work, a global collaboration where success is measured in fleeting discoveries. And yet, when something like 3IATLAS appears, it electrifies the entire community. For a few weeks, humanity gets to reach across the cosmic gulf and briefly touch something from another star. Then, just as quickly, it's gone. A trail of photons fading into the night. But those photons don't vanish in vain. They become knowledge, memory, a small addition to our growing map of the universe. That's the beauty of this detective work. It turns transience into understanding. The object leaves, but the insight stays. Each fleeting visitor teaches us a little more about how worlds form, how they fail, and how everything, even the briefest of encounters, adds to the grand narrative of existence. So yes, studying 3IATLAS was like doing cosmic forensics on a suspect that's already left the crime scene. The clues were faint, the evidence scarce, and the timeline short. But from those scraps, we built a story about motion, chemistry, fragility, and persistence. And that's what astronomy really is. Not just looking up, but listening carefully to what the universe leaves behind when it passes through. When 3IATLAS drifted through our solar system in 2020, it wasn't arriving alone in concept. It was the third entry in a strange new category of cosmic visitors. Before it came Oumuamua and Borisov, two interstellar objects that had already rewritten the rules of astronomy. Together, these three form a kind of galactic family. Distant cousins who don't look alike, don't behave alike, and probably don't even like being compared. But they share one extraordinary trait. None of them belong here. They're outsiders, travelers from other stars, each bringing a piece of their home systems with them. If the solar system were a classroom, they'd be the exchange students from different galaxies, showing up mid-semester with stories no one quite understands. Oumuamua was the mysterious one, sleek, shiny, and strangely shaped. Borisov was the overachiever, a textbook-perfect comet that looked exactly how astronomers hoped an interstellar visitor would. And 3I-ATLAS? It was the one that fell apart on day one. Let's start with the first arrival, Oumuamua, discovered in 2017. It was the first confirmed interstellar object ever detected, and it immediately caused a stir. Unlike any asteroid or comet we'd ever seen, Oumuamua didn't display a tail of gas and dust. It was dark, elongated, and oddly reflective, like a slab of metallic rock, or perhaps an enormous fragment of something larger. Some astronomers described it as cigar-shaped. Others thought it was more like a pancake. Either way, it was thin and tumbling, spinning chaotically as it zipped through the inner solar system at nearly 200,000 kilometers per hour. The weirdest part? It accelerated slightly as it left. Not enough to call it an engine, but enough to make scientists scratch their heads. Comets can do that when gases vent off their surfaces, but Oumuamua didn't show any visible outgassing. Cue the headlines. Alien probe? Extraterrestrial sail? Space rock or spacecraft? The world collectively leaned in, and for a few months, this anonymous object from another star had more publicity than most pop stars. The leading explanation now is less flashy, but no less fascinating. Oumuamua may have been a fragment of a hydrogen iceberg, a chunk of frozen hydrogen that evaporated too quickly to produce a visible tail. Or perhaps it was made of nitrogen ice, chipped off a distant Pluto-like world. Either way, it was an object shaped and sculpted by the conditions of another star system entirely. A foreign geology that entered ours like a whisper. Then, just 2 years later, came 2I Borisov, and this time, there was no mystery about what it was. Borisov was a comet, in every familiar sense of the word. A nucleus, surrounded by a glowing coma, with a tail stretching behind it like a signature in light. Discovered by amateur astronomer Gennady Borisov in Crimea in 2019, it was the first interstellar visitor we could study as it behaved normally. It released gas, reflected sunlight, and followed predictable physics. But normal, in this case, still meant extraordinary. Borisov was made of ices more pristine than any comet in our own solar system. Its chemistry hinted that it came from a place colder, richer in volatiles, and far less processed by starlight than anything near the sun, where Oumuamua was mysterious and aloof. Borisov was open and generous. It offered a clear look at interstellar materials in their rawest form, untouched by our sun, forged under a different star's glow. Through spectroscopy, astronomers found cyanides, carbon monoxide, and other molecules common in comets, but in unusual ratios. Borisov wasn't an alien artifact. It was an alien ingredient list, a frozen recipe card from another solar kitchen. And then, like the third act of a cosmic trilogy, 3I-ATLAS arrived. Discovered by the same ATLAS system that had warned of potential asteroid impacts, it seemed at first to be another comet, faint with hints of a tail. But its orbit gave it away as interstellar. and scientists rejoiced. Another chance to study a visitor from beyond. Except this one didn't hold together long enough to be properly examined. Within weeks, 3IATLAS fragmented into smaller pieces, each dimmer than the last. By the time telescopes swung toward it in earnest, it was already disintegrating, a cosmic guest who fainted at the door. Yet even that collapse told us something new. While Oumuamua and Borisov survived their solar flybys relatively intact, 3IATLAS's rapid breakup revealed just how fragile some interstellar debris can be. It may have been older, more brittle, or simply unlucky. Its structure weakened by countless millennia of radiation and micro-impacts. Where Oumuamua was a relic of solidity and Borisov a testament to pristine ice, 3IATLAS was the reminder that not every traveler makes it through the journey. Comparing the three is like examining snapshots from different corners of the galaxy. Each one carries clues about the diversity of planetary systems beyond our own. Oumuamua suggests that rocky bodies can be ejected from inner regions, possibly fragments of shattered worlds. Borisov tells us that icy comets from the outer reaches of foreign systems wander between stars. 3IATLAS shows that not all of them survive. Some crumble under the first kiss of sunlight. Together, they sketch the outline of a galactic ecosystem in motion. Materials endlessly cycling between stars, planets, and the interstellar medium. What's most humbling is how different they are from one another. For centuries, humans assumed other planetary systems would look just like ours. Then, in less than a decade, 3 tiny visitors blew that assumption to dust. If this small sample is any indication, the galaxy isn't uniform. It's wildly creative. One system might produce metallic shards that glide through the dark. Another might spawn pristine comets made of exotic ices. A third might generate fragile planet seeds, doomed to dissolve at first contact with sunlight. And who knows how many more are out there? For every interstellar visitor we detect, thousands probably pass unseen, slipping silently through the outer solar system. Some may be dust. Others could be massive, unseen objects that never come close enough to notice. Each one, though, carries with it the story of its home, a star we may never identify, a history we'll never read in full. So, yes, it's like meeting 3 exchange students from different star systems. One's icy, one's shiny, and one fell apart on day 1. But, together, they've introduced us to the idea that the universe is far more varied and inventive than we ever imagined. The Milky Way isn't just a galaxy of stars. It's a galaxy of experiments, each one trying a new way to make a world. And as fleeting as their visits are, these cosmic guests have changed the way we see everything. They've shown us that we're part of a much larger conversation, one carried not by radio signals or words, but by rocks drifting between the stars, each one saying the same quiet truth. We are connected. If you ever feel unlucky, just remember this. Humanity managed to spot 3IATLAS, a rock a few hundred meters wide. as it drifted through billions of kilometers of space, reflecting barely any light for only a few fleeting weeks. That's like finding a single grain of sand tumbling through a desert storm from another continent. The odds are so small, they might as well come with their own cosmic laugh track. Detecting interstellar visitors isn't just hard, it's borderline impossible. The universe is vast, dark, and deeply uncooperative. The objects we're looking for are tiny, dim, and move fast. They don't orbit the sun, so we can't predict where they'll be. They appear from nowhere, zip through the inner solar system at breakneck speeds, and then vanish forever. If the cosmos had a stealth mode, these rocks are using it. For every one we spot, 1,000 probably slip by. Stealth mode engaged. So, let's talk about the numbers. Astronomers estimate that, at any given moment, our solar system might contain a few interstellar objects passing through. Visitors like Oumuamua, Borisov, or 3IATLAS, quietly coasting past Pluto's orbit and heading back out again. The problem is, almost none of them ever come close enough or shine bright enough for our telescopes to notice. To put it in perspective, the average interstellar object might be just a few hundred meters across, dark as charcoal, and traveling at tens of kilometers per second. Out beyond the inner solar system, sunlight is so weak that these rocks barely reflect anything. By the time one gets close enough for detection, it's usually too late. It's already heading back out. Astronomers liken it to trying to photograph a fly buzzing through a pitch-black warehouse using a camera that takes one picture every few hours. Yet, somehow, we've done it 3 times so far. And from those 3 data points, scientists have started doing what scientists do best: building models, crunching probabilities, and asking big, uncomfortable questions. If we've seen 3 in less than a decade, how many are really out there? The math suggests an astonishing number. Based on detection rates and survey coverage, researchers estimate that the Milky Way could contain billions of interstellar objects per cubic light year. That's right, per cubic light year. Most are small, perhaps the size of pebbles or boulders, drifting unseen between stars. They're not rare visitors. They're the cosmic background noise of a galaxy forever shedding its excess material. Every time a solar system forms, it throws out countless leftovers. Planetesimals that got too close to giant planets, comets that took a wrong turn, fragments from collisions. Multiply that by hundreds of billions of stars, and the galaxy becomes a vast sea of exiles. Now, the trick isn't that they exist, it's catching them in the act. Our current detection methods are like fishing nets with enormous holes. Ground-based telescopes like Pan-STARRS, ATLAS, and the Catalina Sky Survey scan the skies nightly, but they can only catch objects that reflect enough light and move within certain angles of view. Most interstellar rocks pass by unnoticed, either too faint, too distant, or too fast. Statistically, we're missing nearly all of them. It's not just about brightness, it's about geometry. Space is big, and the solar system is tiny by comparison. The chance of an interstellar traveler aligning just right to pass close enough to Earth for us to see it is microscopic. Most fly by millions of kilometers away, never coming within range of our telescopes. It's like tossing billions of darts across the entire planet and hoping one lands perfectly on a coin in your backyard. And yet, even those rare detections have revolutionized what we know. From Oumuamua's mysterious acceleration to Borisov's pristine ices to 3IATLAS's fragility, each one has offered a unique glimpse into the diversity of planetary systems beyond our own. But here's the wild part. If we've already seen 3, it implies we're just scratching the surface. The galaxy might be teeming with these silent travelers, constantly flowing between stars in numbers too vast to truly comprehend. Upcoming observatories may finally change that. The Vera C. Rubin Observatory, for instance, is set to scan the entire visible sky every few nights when it comes online. Its deep, wide-field vision will make it far easier to catch faint, fast-moving objects like interstellar visitors. Some estimates suggest it could detect dozens per year. If that happens, we'll finally start turning statistics into stories, building a real census of these wandering worlds. But even with the best technology, there's a sense of humility in the math. For every rock we catch, countless others glide by unseen. Some might skim the edges of the solar system without ever being noticed. Others could pass close enough that, for a few hours, they'd cast shadows on our instruments, only for us to realize it years later, buried in archived data. The thought is both exhilarating and a little eerie. The universe is constantly sending us visitors, and we barely notice. And that's the paradox of cosmic detection. We're a species confined to a small planet, staring into the dark with mirrors and math, trying to make sense of a universe that doesn't particularly care about being seen. But every once in a while, we get lucky. A rock like 3IATLAS drifts close enough, reflects just enough sunlight, and suddenly we're handed a mystery. For a few brief weeks, humanity and the cosmos share a moment of acknowledgement before the object vanishes again into the infinite night. It's almost poetic how improbable it all is. The sheer statistical unlikelihood of spotting these travelers mirrors the odds of life itself. Rare, fragile, and fleeting, yet somehow real. Our telescopes, our models, our restless curiosity, all of it exists because we refuse to accept that the universe is too big to understand. We keep looking, keep counting, keep widening the net. So, yes, for everyone we spot, 1,000 probably slip by, silent, invisible, and indifferent. But that's okay, because even if we only ever catch a few, each one reminds us that the impossible isn't as unreachable as it seems. Sometimes the universe blinks, And for a moment, we see something extraordinary. Every time an interstellar visitor streaks through our solar system, humanity's collective instinct kicks in. Chase it. Don't let it get away. Point every telescope, fire up the engines, and somehow, go after that cosmic tourist before it vanishes into infinity. The problem is, these things move fast. By the time we spot them, they're already on their way out. It's like trying to flag down a speeding car after it's already past the exit ramp. Still, the question remains irresistible. Could we ever actually catch one? Right now, the answer is maybe, if we plan way ahead and get a little lucky. When Oumuamua flew by in 2017, it left scientists exhilarated and mildly exasperated. Here was the first confirmed interstellar object ever seen, zipping through our cosmic backyard, and all we could do was watch it fade away. By the time we realized how special it was moving too fast, about 87 kilometers per second relative to the Sun, for any existing spacecraft to catch up. We were the cosmic equivalent of people standing on the sidewalk, watching a UFO disappear over the horizon, muttering, "Next time, we'll be ready." Then 2I Borisov came along in 2019. Another chance, another visitor. But again, it was already racing past at over 30 kilometers per second. Still far beyond the reach of anything we could launch on short notice. The fastest spacecraft humanity's ever built, NASA's Parker Solar Probe, tops out around 190 kilometers per second at its closest approach to the Sun, but only after years of gravity assists. The catch? It's not designed to steer toward random comets. It's on a fixed, sun-kissing trajectory. Chasing an interstellar object would require a completely different kind of spacecraft, one ready to sprint at a moment's notice. That's where the dreamers come in, the engineers, physicists, and futurists who looked at these missed opportunities and said, "Okay, let's build a trap." Enter the idea of an interstellar object interceptor, a spacecraft designed not to sit on the launch pad waiting for one specific target, but to wait in space, like a cat crouched near the door. One real mission inspired by this vision is the Comet Interceptor, a European Space Agency, ESA, project scheduled for launch in the late 2020s. Its plan is beautifully simple. Send a spacecraft to park at a gravitationally stable point near Earth, a Lagrange point, and have it wait. The moment a promising object, maybe a comet, maybe an interstellar visitor, is detected entering the inner solar system, the interceptor will pounce. It can quickly adjust course, race toward the target, and release small probes to fly through its coma, capturing images and samples before it disappears. If 3IATLAS or Oumuamua had been discovered with such a craft already waiting, we could have had close-up photos, direct chemical analyses, and maybe even samples of alien dust. Instead, all we have are pixels and spectra. But the next time a cosmic tourist drifts through our neighborhood, the Comet Interceptor might be ready. waiting with a metaphorical butterfly net, yelling, "Wait! We just want to scan your atoms." There are more ambitious proposals too, some bordering on science fiction, others inching toward feasibility. NASA's interstellar probe concept, for example, envisions a spacecraft that could travel hundreds of astronomical units. That's hundreds of times farther than Earth is from the Sun, to study the outer reaches of the solar system and beyond. With enough speed, it could potentially intercept or rendezvous with an inbound interstellar object on its way through. Then there's Project Lyra, a plan hatched almost immediately after Oumuamua's discovery by a team of researchers from the Initiative for Interstellar Studies. Their audacious goal: launch a spacecraft fast enough to catch up to Oumuamua after it had already left. The math was unforgiving. It would require launch speeds of tens of kilometers per second, and possibly gravity assists from Jupiter and the Sun. But technically, it wasn't impossible. Just very, very hard. The mission would take decades, but if successful, it could mean humanity's first physical encounter with an object from another star. Other ideas push the boundaries of imagination. Solar sails powered by sunlight or lasers, capable of reaching enormous velocities. Nuclear-propelled probes that could accelerate continuously. Or fleets of miniature, ready-to-go spacecraft stationed throughout the solar system, ready to chase any interstellar interloper the moment it's spotted. It's the astronomical equivalent of keeping a dozen race cars idling at the starting line, just in case someone shouts, "Go!" But beyond the excitement and engineering challenges lies a philosophical question. Why chase them at all? The answer is simple and deeply human: curiosity. These objects are time capsules, fragments from distant planetary systems. Studying one up close would be like holding a piece of another star in our hands. It could tell us what other worlds are made of, how they form, and how similar or different they are from our own. It could even reveal organic molecules, forged light years away, offering new clues to how life's ingredients spread across the cosmos. To catch one, though, we'll need readiness, speed, and luck. The first two are engineering problems. The third is patience. The odds are that we'll see another interstellar visitor within the next decade or two. The real question is whether we'll be ready this time. Whether we'll have a spacecraft fueled, waiting, and flexible enough to chase it. Because once these objects come and go, they're gone forever. No return visits, no second chances. Each one is a fleeting messenger from elsewhere, carrying secrets we can only guess at. And if we ever manage to catch one, to fly alongside it, to sample its dust, to photograph its alien surface, it would be one of the most profound moments in human history. After all, we've sent probes to the Moon, Mars, and even beyond the solar system, but chasing something from another star. That would be different. That would be us reaching across the cosmic gulf and saying, "We've been waiting for you." It's a thrilling, humbling goal, to intercept a rock that's traveled for millions of years, only to spend a few hours in our company. And when that day comes, when the images start streaming back and the data pours in, we'll finally have more than guesses. We'll have a handshake, fleeting, scientific, and spectacular, with another solar system. And maybe, just maybe, we'll send one back someday. Every time humanity discovers a new interstellar visitor, a faint dot of light barely distinguishable from static, something ancient stirs in us. People who have never touched a telescope suddenly find themselves reading about orbital mechanics. News anchors start saying hyperbolic trajectory with surprising confidence. School kids cut out paper comets and tape them to classroom ceilings. It's funny how a piece of debris can make 8 billion people look up and feel small in the best possible way. Why do we care so much about a rock? Why does a lump of ice and dust from a place we'll never visit captivate our species for weeks, sometimes months? After all, it's not gold or treasure. It's not a new planet to colonize or a threat to worry about. It's just there, passing by. And yet, for reasons that have less to do with science and more to do with something deeply human, we can't help but chase it with our eyes, our telescopes, and our imagination. Part of it is curiosity, that restless spark that has always defined us. Since the first humans watched the stars from campfires, we've wanted to know what's out there. We built stories around constellations, crafted myths about wandering lights, and eventually replaced those myths with mathematics. But the feeling never changed. The same awe, the same hunger to understand. Interstellar objects like 3IATLAS simply rekindle that instinct. They're the universe dropping by unannounced, knocking on the window to remind us how big it really is. Another reason is connection. When a visitor like 3IATLAS appears, we realize, perhaps more clearly than at any other time, that we're not isolated. For billions of years, we've imagined the stars as distant, unreachable points. But here comes a physical piece of one. It's not light years away. It's here, in our backyard, a fragment of some faraway system sharing space with us for a brief moment. That realization makes the cosmos feel less like a backdrop and more like a living network. A vast web where everything, from stars to dust to people, is part of the same conversation. We also care because these visitors mirror us. They're wanderers, travelers, survivors. 3IATLAS, Oumuamua, Borisov. Each one spent eons alone in the dark, crossing the infinite to arrive uninvited and unannounced. In their stories, we see echoes of our own. Humanity, too, is adrift, a species flung outward by curiosity and chance, trying to find meaning in motion. When we study these wayward objects, we're really studying a reflection of ourselves, fragile, temporary, but determined to make the journey count. And then there's wonder, that rare, irreplaceable emotion that modern life tries its best to flatten. We live surrounded by screens, routines, and noise, But when an interstellar object appears, it cuts through all that like a clean breath of infinity. For a few weeks, the universe reminds us that it's still capable of surprise. Scientists talk numbers, journalists talk stories, artists talk metaphors, but the underlying feeling is the same. We are looking at something that has traveled across light years, just to flicker in our sky. It's humbling in a way that feels good. Not the kind of smallness that comes with insignificance, but the kind that expands the imagination. Standing under that endless canopy of stars, knowing that one of them sent us a visitor, we can feel both tiny and extraordinary at the same time. Tiny, because we're just a speck in a galactic ocean. Extraordinary, because we're a speck that noticed. Out of all the lifeless rocks, icy fragments, and random collisions that have ever happened, we are the ones who looked up and said, "There it is." This is the strange paradox of humanity's relationship with the cosmos. The more we learn, the smaller we seem. And yet, the smaller we seem, the more astonishing our curiosity becomes. The universe might not have built us for understanding, but we insist on trying anyway. We build telescopes that can see galaxies being born. We launch probes to the edge of the solar system just to hear what the silence sounds like. And when a rock like 3IATLAS passes through, we assemble a global orchestra of scientists, engineers, and dreamers to chase it, measure it, and wonder about it together. That shared effort is, perhaps, the most beautiful part. No single person owns the stars, yet every one of us can look at them. When 3IATLAS was discovered, observatories from around the world coordinated instantly. Data poured in from continents and orbits, stitched together by people who spoke different languages, but shared the same sense of awe. For a brief moment, humanity remembered what it's like to unite, not against something, but towards something, a mystery too big for borders. It also says something quietly profound about how we define meaning. Most of what the universe does has nothing to do with us. Stars explode, galaxies collide, planets form and die, all indifferent to human drama. But the instant we observe them, they become stories, not just cosmic events, but part of our shared narrative of discovery. That's the secret power of science. It doesn't just reveal facts, it transforms the universe into something that feels intimate. Every observation is a way of saying, "We were here, we saw this, we understood a piece of it." So what does 3IATLAS say about us? That we are endlessly curious, that we find meaning in motion, that even a fragment of stone drifting from another sun can make us pause, point, and feel connected to something immeasurably larger. It tells us that despite the chaos, confusion, and noise of daily life, we still have the capacity for wonder, the one emotion that makes intelligence worthwhile. We'll never meet the star that birthed 3IATLAS. We'll never know the full story of its journey, but maybe that's okay. Its gift wasn't knowledge alone, it was perspective. It reminded us that even in an age of algorithms and instant answers, there are still mysteries big enough to stop us in our tracks. Because in the end, the universe doesn't send us postcards with words. It sends us fragments, bits of matter that drift into our skies for a heartbeat of cosmic time. And when we look up and notice them, when 8 billion people collectively feel a flicker of wonder over a rock that came from nowhere, it tells us something essential about who we are. We may be small, but we're paying attention. And maybe, in a universe this vast, that's the most meaningful thing any species can do. When 3IATLAS first appeared in our skies, it wasn't much to look at, a faint smudge of light drifting through the night, breaking apart almost as soon as it was found. It didn't stick around long enough to show off, didn't survive long enough to be studied properly, and didn't do anything we'd call impressive by cosmic standards. If the universe handed out report cards, this rock would have gotten incomplete. And yet, for all its failures, 3IATLAS accomplished something extraordinary. It made us look up. That's no small thing. In a world saturated with noise, deadlines, and distractions, something as simple as a fragment of interstellar rubble managed to silence humanity for a moment and turn our attention outward. It's ironic, really. A rock that couldn't hold itself together somehow held our collective imagination together instead. Maybe that's its true legacy. From a scientific standpoint, 3IATLAS didn't add much data. It arrived, it crumbled, it left behind some questions and a few blurry images. But from a human standpoint, it gave us something far more valuable: perspective. It reminded us that we live in a universe that is constantly in motion, constantly throwing surprises our way, constantly reminding us that we're part of something bigger. It's easy to forget that between commutes, emails, and grocery lists, we're passengers on a small planet orbiting an ordinary star in a galaxy filled with billions of others. Then, a visitor like 3IATLAS shows up, and suddenly, the cosmic stage lights up again. Maybe that's what makes these interstellar visitors so powerful. They arrive without warning, without purpose, without fanfare. They don't ask for attention. They simply exist. And in doing so, they awaken something in us that's older than language, the instinct to wonder. When we chase them with telescopes, write about them, or even give them names, we're not just studying them, we're connecting to them. They become part of our story, even if only for a moment. And perhaps that's what 3IATLAS was meant to do all along. Not to become a planet, or cradle life, or orbit a star, but to drift just far enough and long enough to cross paths with a curious species that would notice it. In its failure to become a world, it succeeded in sparking worlds of thought in minds scattered across Earth. It became a seed of imagination rather than a seed of matter. And for a fragment that spent millions of years alone in the dark, that's not a bad ending. It's funny how the universe works like that. Success and failure mean something very different out there. Stars explode so that new ones can form. Planets collide to make moons. Chaos births order, and order collapses back into chaos. There's no cosmic scoreboard, no neat categories of triumph and defeat. There's only motion, transformation, and endless experimentation. In that sense, calling 3IATLAS a failed planet feels almost unfair, as if the universe had a checklist it forgot to complete. Maybe it wasn't a failure at all. Maybe its purpose was simply to remind us that creation doesn't always mean completion. Some things exist just long enough to start a chain reaction of curiosity, of thought, of wonder. Maybe it wasn't a failed seed after all, just one that grew into questions instead of worlds. Think about that for a second. For all we know, there are billions of 3IATLAS-like objects out there, each carrying its own story. Some may crash into distant planets, seeding them with the building blocks of life. Others may dissolve into dust before anyone ever sees them. But every one of them represents possibility, the universe's way of trying again, of scattering potential into the dark and seeing what takes root. It's a cosmic kind of persistence, one that mirrors our own. Because, in a way, humanity isn't so different. We send our own seeds into space, probes, signals, bits of data, hoping that somewhere, someone might notice. We build machines to listen for whispers from the stars. We launch telescopes to peer into the distant past. We plant our questions like seeds, never knowing if they'll grow into answers. The universe throws rocks. We throw curiosity. Maybe that's the conversation. One side speaking in matter, the other in meaning, and perhaps that's why we found beauty in something like 3IATLAS. It reminded us that even in a cold, indifferent cosmos, significance isn't measured by permanence. It's measured by impact, not physical, but emotional, intellectual, existential. This unassuming piece of debris entered our solar system, burned briefly in our awareness, and vanished forever. But in that fleeting moment, it made us talk about stars and origins and possibilities. It reminded us that the universe is still capable of surprise, even in an age when we think we've mapped everything. That might be the most human reaction imaginable, to take a cosmic accident and turn it into poetry. To look at a fragment of dust and see a mirror for our own fragile existence. To recognize in something utterly alien the same pattern we live by. A cycle of trying, breaking, and becoming. So, the next time an interstellar object sweeps through our skies, we'll point our instruments, crunch the data, and maybe even design a mission to chase it. But beneath the calculations, we'll be doing something older and simpler, wondering, because that's what we do best. 3IATLAS may not have become a planet, but it became something arguably better. A spark. A reminder that even the smallest, most fleeting things can inspire infinite thought. A seed that didn't grow into a world, but into wonder. And when you think about it, that's a kind of success the universe probably understands better than we do. After all, stars fade, planets die, and comets disintegrate. But curiosity? That's the one thing in the cosmos that seems to resist entropy. It spreads, it evolves, it lasts. So here's to 3IATLAS, the planet that never was, the traveler that never stayed, the messenger that didn't know it had a message. In falling apart, it reminded us how to stay curious. And maybe that's the whole point. In a universe where everything eventually drifts apart, the real creation happens not in what endures, but in what inspires.